In a balanced three-phase four-wire Y system, current can indeed flow on the neutral conductor. While ideally, in a perfectly balanced system, the currents would cancel out, real-world scenarios introduce imbalances. These imbalances, even slight ones, lead to current flow in the neutral. The neutral conductor is considered a current-carrying conductor under specific circumstances, primarily when nonlinear loads are present or when the phase loads are unbalanced. Nonlinear loads, such as those created by computer equipment and some inductive lighting, introduce harmonic currents into the system. These harmonic currents, particularly the third harmonic and its multiples, are additive in the neutral conductor, which can cause significant current flow, potentially exceeding the phase currents. Even with linear loads, if the current draw on each of the three phases is not equal, an unbalanced condition exists. This imbalance results in current flowing through the neutral to compensate for the difference in phase currents. To determine whether the neutral conductor needs to be considered a current-carrying conductor for ampacity purposes, several factors must be evaluated. Firstly, assess the presence and magnitude of nonlinear loads. If nonlinear loads are present, the neutral conductor must always be considered a current-carrying conductor. The increased harmonic currents generated by these loads will significantly increase the neutral current. Secondly, consider the balance of linear loads. In theory, balanced linear loads should not produce neutral current. However, achieving perfect balance is practically impossible. Small variations in impedance while load on each phase will create some degree of imbalance and thus some current in the neutral. Therefore, it is generally recommended to treat the neutral as a current-carrying conductor even with predominantly balanced linear loads, providing a safety margin. Thirdly, if the linear loads are unbalanced, the neutral conductor will undoubtedly carry current. The magnitude of this current will depend directly on the degree of imbalance between the phase currents. A substantial difference in current draw between the phases will result in a correspondingly high neutral current. Nonlinear loads distort the current waveform, introducing harmonics. These harmonics are multiples of the fundamental frequency, typically 60 Hz in the United States. The third harmonic, at 180 Hz, is particularly problematic in three-phase systems. In a balanced three-phase system, the fundamental frequency currents cancel out in the neutral. However, the third harmonic currents are in phase and do not cancel. Instead, they add together in the neutral conductor. This additive effect can result in a neutral current that is significantly higher than the individual phase currents, leading to overheating and potential failure of the conductor if it is not properly sized. As a general guideline, if the nonlinear load exceeds 20% of the total load, the neutral conductor should be considered a current-carrying conductor. This threshold is a general recommendation, and it is essential to consult with a qualified electrician or electrical engineer to perform a thorough analysis of the specific system requirement. This analysis should include a load calculation, harmonic analysis, and consideration of the specific types and characteristics of the connected loads. To accurately size the neutral conductor, several factors need to be considered. Firstly, determine the total load on each phase, including both linear and nonlinear components. Secondly, perform a harmonic analysis to determine the magnitude and frequency of the harmonic currents generated by the nonlinear loads. Specialized equipment, such as a power quality analyzer, can be used to measure these harmonic currents. Thirdly, calculate the expected neutral current based on the phase currents and the harmonic content. This calculation may require specialized software or the assistance of an electrical engineer. Fourthly, select the conductor size that is adequate to carry the calculated neutral current continuously without exceeding its ampacity rating. The ampacity rating of a conductor is the maximum current it can carry safely without overheating. The National Electrical Code, or NEC, provides tables and guidelines for determining the ampacity of conductors based on their size, insulation type, and installation conditions. Fifthly, consider derating factors. The ampacity of a conductor may need to be derated based on factors such as ambient temperature, the number of conductors bundled together, and the presence of harmonics. The NEC provides specific guidelines for derating conductors under these conditions. For example, NEC Table 310.15b3 provides adjustment factors for the number of current-carrying conductors in a raceway or cable. These adjustment factors reduce the ampacity of the conductors to prevent overheating due to the increased heat generated by multiple conductors in close proximity. Similarly, NEC Section 310.15c provides adjustment factors for ambient temperature. These adjustment factors reduce the ampacity of the conductors to account for the increased resistance and heat generation at higher temperatures. When dealing with harmonic currents, NEC Section 220.61 cone requires that the neutral conductor be sized to carry the maximum unbalanced load, including the harmonic currents. In many cases, this may require a neutral conductor that is larger than the phase conductors. Ignoring this requirement can lead to serious safety hazards, including overheating, insulation damage, and fire. Furthermore, it's important to understand that different types of nonlinear loads generate different harmonic profiles. For example, switch-mode power supplies, commonly found in computers and electronic devices, typically generate significant amounts of third harmonic current. Variable frequency drives, used to control the speed of motors, can generate a wider range of harmonic frequencies. The specific harmonic profile of a load will influence the neutral current and the overall power quality of the system. To mitigate the effects of harmonic currents, several techniques can be employed. Firstly, harmonic filters can be installed to reduce the magnitude of the harmonic currents. These filters are typically tuned to specific harmonic frequencies and provide a low impedance path for the harmonic currents, preventing them from flowing through the neutral conductor. Secondly, using phase-shifting transformers can help to cancel out harmonic currents. Phase-shifting transformers create a phase shift between different transformer windings, which can be used to cancel out specific harmonic frequencies. Thirdly, specifying equipment with low harmonic distortion can reduce the generation of harmonic currents at the source. Many manufacturers now offer power supplies and other equipment that are designed to minimize harmonic distortion. Fourthly, oversizing the neutral conductor can provide additional capacity to carry harmonic currents without overheating. This approach is a simple and effective way to mitigate the risks associated with harmonic currents, although it may not be the most cost-effective solution in all cases. In summary, determining whether the neutral conductor in a three-phase 4-wire Y system needs to be considered a current-carrying conductor requires a careful evaluation of the load characteristics. The presence of nonlinear loads, unbalanced phase currents, and harmonic distortion all contribute to neutral current. Following NEC guidelines and consulting with qualified professionals will help ensure that the neutral conductor is properly sized and protected, minimizing the risk of overheating and ensuring the safety and reliability of the electrical system. The considerations don't stop there, however. If the system includes a generator, the neutral grounding is crucial. A properly grounded neutral provides a return path for fault currents, allowing protective devices to operate correctly and clear the fault quickly. A proper grounding can lead to overvoltages, equipment damage, and safety hazards. Also, surge protection devices, or SPDs, protect sensitive electronic equipment from voltage surges caused by lightning strikes or other transient events. SPD are typically installed at the service entrance and at downstream distribution panels to provide comprehensive surge protection. Proper grounding is essential for the effective operation of SPD. Power quality monitoring is also essential for identifying and addressing power quality problems, including harmonic distortion, voltage sags, and voltage swells. Power quality monitors can be installed to continuously monitor the electrical system and provide real-time data on power quality parameters. This data can be used to identify potential problems and implement corrective measures before they cause equipment damage or downtime. The installation and maintenance of electrical systems should be performed by qualified electricians who are familiar with the NEC and other applicable standards. Proper installation and maintenance are essential for ensuring the safety and reliability of the electrical system. Routine inspections should be conducted to identify potential problems and perform necessary repairs. Furthermore, consider the specific application and environment. For example, in data centers and other critical facilities, power quality is of paramount importance. These facilities typically require robust power quality monitoring systems, harmonic filters, and other power quality mitigation measures. In industrial environments, the presence of heavy machinery and variable frequency drives can create significant harmonic distortion. These environments may require specialized harmonic analysis and mitigation techniques. In commercial buildings, energy efficiency is often a major concern. Power quality problems can increase energy consumption and reduce the lifespan of equipment. Implementing power quality mitigation measures can improve energy efficiency and reduce operating costs. Finally, consider the future needs of the electrical system. As technology advances and new equipment is added, the load on the electrical system may change. It is important to design the electrical system with sufficient capacity to accommodate future growth and changes in load characteristics. Periodically re-evaluating the electrical system and implementing necessary upgrades will help ensure its continued safety and reliability. Remember to consult with a qualified electrical engineer to get their advice and knowledge for your particular power distribution system requirements.